Thank you all for coming to the IAS seminar. So today we are very honored to have Professor Jean-Marie Lin to give us a talk. So Jean-Marie Lin is a senior fellow in the Hong Kong Institute for Advanced Study. He is also a professor at the University of Strasbourg, a member of the French Academy of Science, and of course, every one of you should know already. So he's the Nobel Prize laureate in chemistry in 1987. Along with Donald Cram and Charles Patterson for his synthesis of the cryptand, which are a cage-like molecule that can selectively bind other molecules. So Professor Lin's work has significantly advanced the understanding of molecular recognition and self-assembly processes. And currently, as mentioned, he is a professor in the Strasbourg, University of Strasbourg, and he has published more than 1,000 scientific publication contributing extensively to the field of chemistry and material science. So without further ado, I make it short so Professor Lin can share with us his insight, his inspiration, and also to get more time to interact with the young scientists over here at the City University of Hong Kong. So please, Professor.
So does it work nowadays? Oh, it works. It looks like. Okay. Good. Nice to be back. After 6 years. 5 years for the rest of the country up north, mainland as it's called. 6 years here, because at that time, 2019, I had to go directly from Guangzhou to the airport of Hong Kong, for reasons you may remember. So it's nice to see the new institution here with this very nice accommodation upstairs for this very nice room. And I'm very impressed also to have in the audience the person who started it all, Philippe Ciarlet, a mathematician. All my respects. A mathematician who couldn't continue working in France. So he said, all right, why France? He came here and he started an exchange between France and CTU, Hong Kong. So we just talked about it. The first speaker was Philippe Kourilski, who was a colleague at the Collège de France, Claude Cohen-Tanouji, who was the sort of the father of that person over there, and myself after that, and then others, I don't remember. There were some other, Pierre Lyons was also here, yeah. Okay, so I'm also impressed having the presence of another eminent physicist. So this will be hardcore chemistry. Okay. So what I would like to say to you is a bit the sort of way, with an introduction which is very general, and then jumping into what we are doing now. So, steps towards complex matter. That's quite a program. And I would lead you to some of the steps. First of all, we have to start very early on. 13.7 billion years ago, there was as physicists say, a quantum fluctuation or something like that, and our universe started. And right after, there was an enormous inflation, which is now experimentally based, thanks to the machine you see here, down here. That machine here, which according to cosmologists, physicists, has given now solid experimental indication about the theory of inflation. Not just because I think it's also for you something to learn. I'm not a cosmologist, I just read it. But they say, and what can I do? I can just accept it, that our universe increased in size by a factor of 10 to the 78 to 80, something like that, in 10 to the minus 36 seconds. It's difficult to imagine, but that's the way which fits the present picture of cosmology. We could discuss, I have read a little bit about it, but there are many cosmologists in the audience who know much more than I know. So after that, then of course there was no chemistry at that time. Chemistry did not exist at that time. The age of physics started, where the universe was so hot, no chemistry, particles formed, particles got together, make atoms, atoms got together and make molecules. So the age of chemistry starts around here in our universe, and then molecules formed. They, by purely non-living, nothing living, by purely physical processes, became more and more complex, and again they rearranged, and the laws of physics governed the whole thing, so that chemistry could develop more and more in more and more complex fashion. At some stage, they formed particles for containers, like a soap bubble, for instance, which is rather simple chemistry. And then a new feature appeared, a new property appeared on our planet, Earth, which is life on Earth. That's pretty important. We don't yet know how it happened, but since we exist, we will know. Look, I mean, I turn it around. I don't say, we don't know. No, we will know. That's quite clear. Since we exist, we will know. It's evident. So this is the age of biology. But it didn't stop here, luckily. Otherwise, we would not be sitting here. The next step is the most important. Not biology, of course, is a necessary step, but the most important is this one, thinking, which is represented by this very famous statue of Auguste Rodin, as you would say. Rodin, we say in French. Who is the thinker. The ability to think is the greatest, most complex feature we know of. Without thinking, we would not be here. And these are for us, maybe on other planets it's different. Maybe at the end of the screen, there's a continuation. Maybe there are other places in our enormous universe where there are organisms which are more advanced than we are, but we're also already pretty good in that respect, as you will see. So these are steps towards life and thought. And they are made possible through science. This slide is not a wrong slide. It's intentionally dark. Why? Because cosmologists tell us that 68% of dark energy, 27% of dark matter, 90% of nothing we know. Darkness. But there's 5% of visible matter. 5%. We are part of that, because that's the matter that matters. I like it in English because it makes it a nice way of saying it, the matter that matters, which is indeed, it's us. And this 5% can try, and is trying, has made a lot of progress in understanding what the rest is. It's quite incredible. That is, for me, the great enigma, which I sort of like to think about, like you, after a drink, you think even more about, and you talk even more about. So, the big question then, I think the most important question, I don't want to antagonize the famous physicist over there. The big question is, how does matter become complex? How can I go from an elementary particle to a thinking organism? Are there higher forms of complex matter, maybe things beyond the way we think? In order to give an answer to this question, this two-legged organism with a brain, the important thing, has invented something which we call science. And if we look at three pillars of science, we see physics deals with the laws of the universe. They try to answer the question, why? Why is it like that? And everything depends on that. Biology deals with the rules of life. These are not laws, they are rules. How does it function? And chemistry, despite the fact that many people think that chemistry is limited to making new molecules, new materials, new nice things, all the clothes you have, this is chemistry, that's chemistry. But it's a more profound thing. Chemistry deals with the bridge between the why and the how. Why is it like that? This is the physics. How it is, this is the rules of life. But how do you go from one to the other? How do general laws, as general as the physics are, which are valid for the whole universe, how can they lead to an organism which can think about these laws and think back on them? So I tell you from the beginning, I will not get an answer, give you a total answer, but I will try at least to lead you through some steps. First of all, there is one word which can be used for describing, giving an answer, at least for having the sense of an answer: self-organization. It doesn't mean anything in some ways because it doesn't explain something, but we understand that it has happened by itself on the basis of the laws of our universe. And one can even claim, and I am ready to claim, that it is a cosmic imperative, that other universe, by its physical laws, is built in such a way that it will necessarily lead to self-organization. It's not an accident. Life is not an accident. Thinking is not an accident. It is an imperative. It will happen somewhere. And if it has happened somewhere, it will happen somewhere else too. So there is a very, very high probability that there are other thinking organisms around. This being said, it's very philosophical in some ways, but I think one sometimes has to think about the basis of what we are doing. So the steps towards increasing complexity are in great, since we are the ones who now think about it, we have to explain how we get there, and we are chemical objects. There's no doubt. Human organisms, the human brain, is a chemical object, based on chemical object. I don't think it's just chemical, but it's based on chemical object. So molecular chemistry is the start. You take atoms, this is, let's say, physics, you put them together, they interact, they make strong bonds, and you make molecules. That is molecular chemistry, which started about, it's admitted, in 1828 by the work of Friedrich Wöhler in Germany, when he made urea from ammonium cyanate and showed that you can, in a laboratory, make a compound which is contained in living organisms without the help of anything special. So, and now, of course, molecular chemistry has developed enormously, and enormously it will continue to develop. Not only are there very nice molecules which have been made, but a lot of drugs, materials, and all that, and it will continue. But then the question is, what about the interaction with these molecules? They come into the field of supramolecular chemistry, where these molecules which are formed, they interact, they get together, and they have a given number of features, like, for instance, the ability to recognize one another. And this is especially important for biology, because in your body, all the molecules have the ability to recognize the partner, or in other words, to say if they bind strongly or not so strongly. And that is very important, because the biological effects depend on recognition with molecules. You would not exist with the molecules didn't know, I used know is not the right term, but didn't have the possibility to fit with other molecules. This was already said many, many years ago by a very famous German chemist, Emil Fischer, when he said they have to fit together like a lock and a key, like Schloss und Schlüssel, a lock and a key. They have to fit together to have an action, to be recognized. That is one of the basic principles of biology. Without lock and key complementarity, you would not have life. And beyond that comes the question, where we go from this. The molecular chemistry is in principle isolated molecules. Supramolecular chemistry is in principle, let's say, assemblies, populations of molecules. And we may call it, for physics, soft matter. Soft matter is of supramolecular level. And then beyond that comes the fact that these objects can lead to self-organization, to the spontaneous generation of complex architecture on the basis of how it is built, how the components are built. I'll give you an example of that in a moment. So it is a spontaneous, but molecular information controlled generation of complex architectures. molecular information control, that means that each entity of those which get together has a given structure. The information is in the molecule, and it's the interaction between them which gives a recognition process, like a lock and a key. Very simple image, very important image, which I think all of us, especially chemists and biologists, have to remember. Now, a very simple example of that is also an infamous one, because it's a virus. The virus is especially infamous right now because we know that the virus was not so good for us recently. And the virus is a self-assembled structure. I give you here the picture of the first virus which was understood, a work by Aaron Klug, who got the Nobel Prize for that. This is a tobacco mosaic virus, which is a spontaneous construction from its bricks of an entity, which is like a sort of a tube, a helical tube, and there is in the middle of the tube is the RNA, the genome of the virus. Note it's also a RNA virus like the COVID one. What is happening here is these are 2,130 building blocks, bricks, which have a given shape, sort of conical, and if you want to put all the conical structures together, it automatically generates a circle, and then it develops. You see on the left-hand side a very simplified version here, very simplified version. On the right-hand side, a more detailed one, where you have a crystal structure, and these are the molecules in question. In this case, it's not, the complementarity is self-complementarity. One side of the molecule is complementary to the other one, so they can attach to each other, and they develop spontaneously. It looks like magic. It's not magic at all. But we understand everything that happens there. It's physical chemistry, chemically, it's interactions, of course. It's physical interactions, structure, the construction of the building blocks, and the way they fit together. So the self-organization, therefore, is the result of storing at the molecular level information in the building blocks, and at the supramolecular level processing this information and let the system run. You don't have to do anything. You just mix and you get. So this looks like a program system. I like to call it this way because nowadays everybody speaks about programs, programming, artificial intelligence comes up also sometimes now. But it's a program system, and we are all programmed. We are biologically, chemically, biologically programmed. Now, self-organization can be on the molecular level, on the supramolecular level, but of course the molecular level is the building blocks, the supramolecular level is then the entity, the final object. And at the beginning, so what I told you here, very, very simply, very quickly, is that by design, one can make building blocks which will then assemble in a given way. And if you change the building blocks, you get something else at the end. So you can call it, if you want to continue to have this language of information science, that information is in molecules, and you can program the system so that it can then run and generate a final architecture. This leads to a controlled generation of molecular and supramolecular entities. Now, the next step in complexity will be to let the system choose what it needs, and this is what I would like more to talk about, what it needs to build itself up. From a diversity of building blocks, let the system do its job. So this is introducing the idea of selection in chemistry, where beyond programming the system will be in contact with a diversity of building blocks and will choose what it needs. For that, you need diversity, different building blocks if you want to choose, and dynamics. You don't want the first collision to be stuck, to be too strong, because then it will not be able to adapt. He will then be stable, it's too stable. So one wants it to be somewhat labile, and one can therefore define a chemistry which is dynamic in its constitution, a chemistry where the basic objects are not stable, so to say, are not blocked in their given constitution, but where they can change constitution. by exchanging components. This provides a new feature of great importance, adaptation. If the conditions changed during the time where this dissociation, association occurs, then maybe the result can be different. There will be adaptation, and I will give you a number of examples which leads to what one can call adaptive chemistry, and that is now our major field of interest, with a twist towards something which is, I find, quite interesting. You will see at the end. So let's come back now to supramolecular chemistry. For a long time, supramolecular chemistry was considered as the systems where there's a material structure, where, for instance, a water molecule is molecular chemistry, a glass of water is supramolecular chemistry, so to say. But one has not considered at that time the fact that all these things, because the interactions are rather labile, they can dissociate, associate, and so on. So this is a dynamic non-covalent chemistry. Non-covalent because it's not what the chemists call a covalent bond, a strong bond. All the chemists here know what a covalent bond is. Non-covalent binding is labile compared to covalent. In most cases, there are some exceptions. And this is a dynamic non-covalent chemistry. Then, by a sort of a twist of looking at, if you look at things, the question came up, what would happen if molecules also become dynamic and can break apart? This can be done if you introduce reversible chemical bonds in the molecule, which can break and reform and break and reform. And this then gives a dynamic covalent chemistry. Now, if you consider that all this is chemistry and the difference between covalent and non-covalent can be put under one heading, then you can call it constitutional dynamic chemistry. It's a bit a complicated wording, but it means exactly what it should mean. The constitution of the chemical object, either molecular or supramolecular, will be dynamic, will be able to dissociate, reassociate, and making therefore possible adaptation by exchange of components, variation in structure, and this is this adaptive chemistry I mentioned. Now, we have then, and now I'm getting into the hardcore chemistry, look for reactions which are reversible, which can be used for doing that, and which are of general interest for trying to investigate this area. First of all, a very simple reaction all chemists should know, must know, is the condensation of an amine with a carbonyl giving an imine, which you see here. And this is, this thing is a bit slow. This is slow electronics. Usually electronics is fast. So this is, okay, I mean, it's not so easy to handle. So you get an imine which leaves water, and as long as water is present, it can go back and forth and back and forth. There's also another mechanism downstairs through an aminal, but this is not so important for the moment. There's another process I want to mention because I need it at the end, which is chemically very interesting. That is now I'm sorry for the complicated names. It's a dynamic covalent Knoevenagel reaction. But for the chemist, Knoevenagel reaction is something they know. It's a reaction where you can condense, where you condense here. That's a Knoevenagel compound. It's a derivative of barbituric acid with here a CC double bond. I'm sorry for the physicist and mathematician, but that's the way it is. So when you mix this with an imine, the interesting thing was, and this was discovered by one of my PhD students from Thailand, when she mixed these things together in non-polar solvents, one gets a very interesting exchange, which is very close in mechanism to the metathesis reaction, which got a Nobel Prize for in completely different systems, where the imine adds on it, forms a four-membered ring with a nitrogen, and then this four-membered ring can either break the bonds which were formed and they go back, that is silent, or it can break the two other bonds. As you can see here, in blue, this is the sign-in process where the bonds which break are the ones which were formed. And if you break the other two, because this can be 1,3, it can be 2,4, then you make an exchange. And that is quite interesting, because you can exchange the groups which were attached to the imide. Okay, so what is it good for? Why do all these things? What does it bring? First of all, the fact that things can exchange, that means that you have a soup of exchanging entities which has a high diversity, which can all the time equilibrate. So you get what is now called a library. In the older times, when I got my PhD, it was called a terrible mixture which you could throw only in the sink. You could not analyze it. Now you can, with the modern methods of analysis, you can know what is going on. It is based, of course, on dynamic diversity, either supramolecular or molecular, and it can operate recognition-induced selection because the objects will recognize. It can be applied to developing methods for biologically active substances, new methods, which I will show you one case, just schematically. It can be implemented in dynamic nanodevices. I will not talk about that. And also in adaptive materials. I will give examples of that before going to the final step. Now, this is also interesting because it merges diversity, which is in fact combinatorics, recombination, just combinatorics, and informatics in the recognition process. And this is quite two powerful tools, generating diversity and performing recognition on this diversity. Now, the example I will give you here, this is very schematic, but it has been applied in a number of generation of biologically active substances. It's very schematic here, but just to give you an idea. Suppose you start with the components you have on the left-hand side. They have different shapes, different colors, so that means they have different structures. These shapes you see, the colors give different structures, different atoms, and so on. And they have a little black dot, which is a functional group which can lead to connections which are reversible. You mix those together, and what do you get? You get access to the space of all possible combinations. You get the components, generate constituents, and the space of all possible combinations. Now, so what do you do with this? This is a mess. So we apply, again, very simple principle of thermodynamics, a physical principle, which is to say, okay, this is called aussi le principe de Le Chatelier. If you add now into this mixture something which can bind, which will be an additional binding agent, then what will happen if it's this receptor? A sort of a recognition process will operate and do something to these constituents. If one of them fits rather well, then it will be amplified. It will be selected from the mixture and amplified. But when it's amplified, of course, all the other ones know it, because what this one amplifies is at the expense of the other ones. So you have this lock and key principle of Emil Fischer. It selects the best binder, which means the lock itself, that's the job to find its key. So the lock assembles its own key. This is in principle very powerful because you don't have to make the system anymore. You let it do. Thermodynamics do it for you. But of course, it's not perfect, but can discuss the limitations in terms of number of things you can do, but it is not exactly what I want to do here. What I can say is that dynamic search of the best binder has been used for first of all, rediscovering inhibitors of enzymes which had been studied, but just as a proof of principle to show that it works, and also for synthetic receptors. For instance, carbonic anhydrase was an enzyme for which the lock and key selection has been used to generate a binder, an inhibitor, which is close to the one which was known. And this can be used for drug discovery. In terms of adaptation, it's a bit low there. It means that there's an adaptation of the dynamic system to the receptor you have added. You have added something, and the whole entity then has to adapt to what has been done. Now, what about materials? Just a few slides on that. Constitutional dynamic materials may, of course, in principle, you say this is stupid to try to make materials which fall apart. If this is an artificial stuff, so if it falls apart, it's not very good for me. Yeah? But it's quite interesting because these materials may have other properties, not the ones which static materials show, but adaptive materials. So if you look at a specific category of materials, polymers, constitutional dynamic polymers can be called dynamers. Dynamers are then of two types. They can be either the supramolecular or the molecular level. On the molecular level, if you have a monomer which has two identical, this is difficult. Anyway, the two yellow things are at the end of a chain, two functional groups. The red circles are two other functional groups which are complementary to the yellow ones, and you can make a chain, a polymer. It gives a polymer. In the case of molecular covalent dynamers, the connection between the yellow and the blue is a reversible chemical reaction. If, on the other hand, you consider the supramolecular level, then the process is physical, not chemical anymore. It's a specific interaction between the yellow and the red functional groups which bind together in a reversible fashion and by recognizing each other. And this has then led to a supramolecular polymer chemistry. I would like to show you some examples of that, because supramolecular polymers did not exist. They existed, of course, because everything existed, but they were not recognized as such before 1990. And I just mentioned that the first paper we had on that was in 1990, and I tell you why. I usually don't cite the dates, but in this case it's an important date. Why? Because in 2013, I got an email from a company in the Netherlands, Xeltis, who told me, oh, yeah, we have made cardiovascular implants from supramolecular polymers. They were based on a variation of supramolecular polymers introduced by Bert Meyer in Eindhoven in the Netherlands. And this polymer was then, they worked on it, they had to develop it, they made it biocompatible, and they made the material out of it which can be used for the surgical reconstruction of the heart of children who had a congenital severe heart malformation. And here then the picture, I like to show it because it's quite fantastic. Here is the first little girl, Dominica, 4 years old, who was implanted in 2013, on October 23, 2013, by Leo Bokliria, a pediatric surgeon, cardiovascular surgeon at the Bakulev Center for Cardiovascular Surgery in Moscow. Both look very happy, and we were very happy too. We hadn't predicted that. But you know, if you have a new class of materials, you know, somebody will find something interesting. If it's not you, it's somebody else. And this here was the group of Xeltis, which was convinced that something can be done with it. They did the work, they got the money and all the steps. This is why it takes 23 years. And of course, then you have to introduce it in a human body. That's not all that easy. You have to find the surgeon who would do it. And you have to have the agreement of the authorities to do so. And when all these hurdles are overcome, then you can do this kind of thing. This is now many more than 10. This is an old slide, of course. They also developed heart valves, pulmonary heart valves. This works less well because a valve has to open and close, and that's for plastic materials, that's a bit of a problem. But they now, recently the news I got is that there are more they are more focusing on making just tubings which can be introduced in the bodies also for dialysis and things like that. But just to tell you that it took 23 years to go from the initial publication to an implantation in the human body. And okay, and a lot of work for lots of people around the world. So a scientist is never alone. And if you don't find it, somebody else will find it. So what about other properties of these dynamic supramolecular materials? Here you see a film which was prepared by one of my postdocs, Dr. Nabarun Roy. And you see 2 fingers. The field is a very nice transparent film, no deformation. And he takes it. And somebody else, of course, he has no 3 hands, he has only 2, cuts the film, and then superimpose the 2 ends, and you press. In this case, since we are technically very primitive, you use a finger, and you just press on it. And then you can stretch, and it sticks. This takes about a few minutes. And it still works. That's what's quite important, because Nabarun did that work many years ago now, 10 years at least. And not so long ago, we said, OK, you still have a sample of your stuff? He said, yes, and it worked, still worked. So this means that self-healing materials can be made, can be done, and it would be quite interesting to develop. And people will explore it, I'm pretty sure. These are just measurements. I don't want to bore you with numbers. What about then the covalent type of dynamos? These were supramolecular polymers of dynamic nature. And now let's look at covalent ones. If you make a film by condensing a bis carbonyl with a bis amine, then you get a chain of polyimine. This is this polyimine here. You get a polyimine chain. So now you can make a film with a given aldehyde, bis dialdehyde and diamine, and a film with another one. So let's call A and B the dialdehyde and the diamine. So you can make AB and A prime, B prime. So you can make a film AB, 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 and a film A prime, B prime, A prime, B prime, A prime, B prime. You superimpose them, and this connection is dynamic. And since it is dynamic, you can now, one can open in one part of the film on the interface between the 2 films. There can be breaking, but reconstitution through the interface. But it can the ones on top can combine with the ones on bottom, therefore generating something new. In the top case, you have one polymer AB, AB, another one A prime, B prime, A prime, B prime. But there are 2 combinations which are absent, A with B prime and A prime with B. And these can now form when they recombine. So that you now have, if you have a reversible binding, a reversible linkage, then this can lead to 2 new compositions. And this may lead to the new properties if A, B prime and A prime B have different properties from the starting materials. And just to give an illustration, optically it's always more interesting because seeing is believing, as some people say. So this was work done by co-workers of Mitsui Chemicals in Japan. They were sending people to the group to do the work, the basic work, and then took it back to Japan to see whether one can develop something out of it which could be commercially interesting. But let's not get into that. So if you have this case, as I said, AB and A prime, B prime, these 2 reversible polymers, where the linkage between the A's and the B's is reversible, then you can get 2 new compositions, AB prime and A prime B, which can either have, one of them has a color, Why not? It can also have fluorescence. And to illustrate that, since they were Japanese co-workers, they liked these nice little pictures. So they took a cat, and the head of the cat and the ears of the cat were AB. The inside of the ears, the eyes, and the whiskers, moustache in French, are the other one. So they are superimposed only in certain regions, and the result is done. Then you get, indeed, color and fluorescence where it is superimposed. This just shows that it works. It gives also some, you also can think about what can you do? You can maybe heat at the interface with heating laser and then write in one dimension. And if you make a millefeuille, you can write in 3 dimensions. Okay. Now, let's go one step further towards adaptive chemistry. Adaptation through variation in constitution, as I said earlier, in a network. Now, the network I will define in a moment. Since all these objects are floating around, it's a network. If we touch one point, the other ones know what's going on at that stage, at that point. I will come back to that. This adaptation can be an adaptation to a change in medium, to a phase change, a physical stimulus, heat, pressure, and so on, or electric field, a chemical effector like protons, like metal ions, and so on, even morphological changes, and so on. These are adaptive chemical systems. Now, the especially interesting case is when this type of variation is driven by self-organization. Then we come back to the beginning to self-organization. And this comes, I don't get into it right now, but it comes back. So the first experiment, which it was in fact not really the first. You know, when you work at this, all the scientists here know that, when your work goes further and further, you change your ideas, they become more clear and maybe more interesting. And then you look sometimes back at what you have done earlier and said, oh, but this was already present in what we had done earlier. So here, so there was some sort of some precedence in the work we had been doing. But this was the most clear illustration. With the lab of Paolo Samori, my colleague doing nanochemistry, we did the following experiment. You take the aldehyde on the top with a long chain, and the 3 different diamines on the bottom with 2 carbons, 6 carbons, 12 carbons between the 2 NH2 groups, B2, B6, B12. And you mix them together. What do you get? As long as you remain in solution, you have something totally uninteresting. You get a mixture of not even bis imines, just it only condenses on one side, monoimines, and it makes a mixture of the 2, the 6, and the 12. Not very funny, not very nice. But then you take just a drop and you deposit it on a surface of graphite, nothing else. You just let it deposit. And you look at it with STM scanning, tunneling microscopy. What do you get? Quite impressive. You get only one compound, which is the bisimine and only the C12. Now, that's not a miracle. What is, it looks extremely complicated, but it's very simple. The adsorption, it happens that among the mixture of things which can form, which are monoimines and diimines of 3 different compounds, one of them has a better adsorption on the surface, and that's the one which forms. So the adsorption on the surface drives the reaction to completion, making double bonds on both sides, and it drives the selection of the one which is the best. It's just physical chemistry or physics, adsorption forces. And this is, yeah, I think there's a little bit something wrong here, but okay, it's all right. Adaptation to surface adsorption. So self-organization on the surface, the fact that the C12 with 2 chains, one on each side, has the best adsorption on the surface, So self-organization drives the selection by picking out the compound which absorbs best, which was not even present at the beginning. Maybe there was 1% or something like that, but here it's the only one you find on the surface. So this is one can say, I don't claim that it has a contribution to the origin of life, which many people are studying, but just to say that the principle of absorbing a complex system on a surface leads already to a lot of selection, complexity, and so on by simple absorption forces. In fact, now I sort of think we should have tried absorbing it not only on graphite, but taking also maybe clay or some other material and see if it's another combination which comes out. So now how do we analyze this type of networks? I have talked about already using this terminology about A prime, B prime, reacting with the A's with the B's and generating AB prime, A prime B, and A prime B prime. Now that's the simplest network you can have, is 4, that one is a square. And you can put these 4 constituents at the corners of the square. Now, if you analyze the relationships between these constituents, what do you find? First of all, that the ones at the corners are linked AB is in such a way that they are antagonistic. In other words, the constituents at the corners share a component. AB shares A with AB prime and A prime and B with A prime B. So if now in some way, of course in a closed system, you have a way to amplify AB. AB can only increase by picking up the A of AB prime and the B of A prime B. So if AB increases, A prime B prime, if AB increases, AB prime and A prime B must decrease, okay? Because AB picks up the A's and the B's. So this is an antagonistic relationship, which is sort of, you say, okay, antagonistic, why not? But it's much more interesting to look at the diagonals. The diagonals, they link constituents which do not share a component. And that means that these are agonists. If AB increases, the increase of AB liberates A prime and B prime, which can make A prime B prime. Therefore, AB, when AB increases, A prime B prime must increase. Or at least all the stuff is present to make it increase. And this is the agonistic relationship. This is, of course, more interesting than the antagonists. So, conclusion, you can adapt if you have a way to modify one of them, the AB, for instance, then you have the whole thing rearranged and adapts. But the most important, this is the term which will come back later, agonist amplification. The agonists, those who do not share a component, will amplify one and the other. So in terms of, let's say, developmental biology even, you can say that the fittest for what you want, for what you impose on it, also amplifies the unfittest for that same thing. In other words, if you apply an agent which amplifies, that means which likes the fittest, but it will also, by the agonistic relationship, amplify the one which is the worst for that thing. But maybe it's interesting for something else. So these are adaptive chemical networks, and I will illustrate some now as in structures. Very simply first, let's go back to this square, a network of 4. We have here, at the beginning, we can make a statistical distribution of an AB, AB prime, A prime B, A prime B prime. And these are now ligands for binding metal ions. And the best binder for chemists here is quite evident. They recognize immediately that AB is the best binder for a metal ion because it has N and O, 3 binding sites, so it will bind well. This is for coordination chemists, that is quite evident, quite clear. So if we then apply a metal ion, the metal ion will pick up, amplify the one which is the best binder. We have also added some amine, a weak base, to ionize the NH, so it makes it even stronger. The result of that is, from the statistical distribution of 4, you come up with 50-50 of the agonists, the one which binds the metal ion the best, and the one which is the worst in binding that metal ion, in agreement with what I said earlier. So the amplification is that due to the metal cation, and if we want to represent it as the network, we start with statistical distribution. The effector is added, it amplifies AB and A prime B prime. It's almost 50-50 because it's very strong in that amplification, an adaptation of the system to the addition of the metal cation. And you have then, again, the AB, the fittest for the metal ion binding, amplifies the unfittest, the worst for metal ion binding. But as I said, that one can be interesting. And we have shown that in cases where, for instance, the agonist has a color which the starting material does not have. So if you apply this process, you will generate automatically the color of the one which you have not touched, just because the other one makes it possible. Well, it eats up the other. Yeah. And now, okay, I wanted to get a bit further. Usually I don't add the slide now to come, it's a bit complicated, but to go to higher orders. You say 4, okay, fine, 4, but what about higher? So we have done, this was in fact a Chinese co-worker, Dr. Quang Wen Men from Jilin University, and this was the question of a 3 by 3. Okay, 3 by 3 is 9. It's not yet very, very high number, but it is, okay, it's better than 4, just 4. 3 by 3 gives 9. And you mix now 3 aldehydes, 3 amines, and you see, you should generate 9 combinations altogether. So, when you just mix them, not very interesting. You get a mixture of partially reacted constituents. You get also some which don't react at all, like the D4, which doesn't react because it's very unreactive type of aminoquinoline. And so, okay, well, so that's not very interesting. Then you start applying metal ions. We operate at air, nothing very, very advanced, very just at air. You add a copper 1, that you will see in a moment why copper 1. Copper 1 is a reduced state of copper, which the normal state of copper, ionic copper, is copper 2. So as soon as copper 1 sees the oxygen, it has a tendency to want to oxidize to copper 2, and copper 2 likes very much the aminoquinoline, so it oxidizes copper 1 to copper 2, which then binds to quinoline, and that's finished. So the thing is, but then you add first iron. If you add iron, iron likes very much the aminoquinoline, and especially on the right-hand side there, you see the constituent which binds very strongly iron. So if you add iron, iron picks up that constituent over there on the right-hand side and amplifies it. As a consequence, you have a subnetwork with a 2 by 2, which is also amplified. And then what happens is that now the aminoquinoline, which was the bad guy, which made the first system initially with copper 1 unstable, you can now add, because that one is gone, iron has picked it up. This dynamic network is the agonist. Now you add copper 1, and you get a very nice single line, straight line of diagonals, where iron 2, copper 1, each of them picks what it prefers, and there's another one, what's remaining, is represented by the purple spot. So you simplify the system enormously. Now, this looks complicated, but I want just to insist on what is behind it. What are the concepts one can find there? Which is very simple. You know, in many chemical experiments, if you think about the experiment, it tells you much more than what you were looking for. What happened here, in fact, is much richer than what looks at the surface. Okay, when you add together copper and iron, it works also, but this is a question of kinetics. So, number one, this is two levels of agonist amplification. First of all, iron amplifies the one A64 and the subnetwork. And then when you add copper, you have another amplification, which is the second agonist amplification. Then the response is conditional to the sequence of effectors. You cannot start with copper and then add iron. Doesn't work, because copper will be oxidized and will destroy the system. But if you start with iron, you eliminate the bad guy, and so copper can do its job. So the result is you have a conditional response to the sequence. Then you have two effectors, effector 1 iron, effector 2 copper. And this is an interesting system, but here I sort of push it a bit. But you know, this is adaptive chemistry. What would be evolutive? Evolution is keeping the characters which have been adapted. And in evolution system, you don't want to go back to thermodynamic equilibrium. You want to go a step further. So you have to acquire something, keep it, and go a step further. And in some ways, that is what happens here. The iron is stable, so you conceive that property of the system to eliminate, to generate one, the one on the right, and then you can go a step further and go to this system which has just one diagonal. Finally, something also sort of startling is that if you look at it, what it happens is that an increase in complexity leads to simplexity. In other words, you add one more entity, and because it's done in a sequential fashion, you end up with a much simpler system. That the complexity is increased by one more metal ion, but the system as a result is much simpler, just 3 constituents remaining at the end. So out of this experiment, we have now done some other experiments which show that this works in many other cases, where indeed, when you have a mixture of competing processes, if you have the right sequence, then you get a much simpler output than if you just let it go. And this is something also, perhaps, which is important in biology. Now, just for illustration also, what time is it? 4. Okay. The question is also, can the change system adapt to phase separation, to change in phase? Here we have a mixture of acetonitrile water, which is a homogeneous solution. And we dissolve in it compounds, which are shown on the bottom here, where you have an aldehyde and an amine, which is blue-blue means hydrophilic, blue-red means hydrophilic, lipophilic, and lipophilic, hydrophilic, and lipo-lipo. These are the compounds are shown here, and that's the distribution you have at the start. When you mix those together, you get given distribution, which is shown there. Then, very simply, this mixture of acetonitrile water, you add some sodium chloride, kitchen salt. Then this kitchen salt makes the phases separate, because the salt prefers water to acetonitrile, and so induces a phase separation in the system, and you get a phase separation, which is shown here. So now the system has to adapt to the fact that now there are 2 phases, and it has to adapt by, it's quite normal, you would think about that. The more lipophilic will go to the organic phase, the more hydrophilic will go to the aqueous phase. And indeed, as you can see here, after adding the sodium chloride, you have a redistribution of the whole thing, where you favor organic lipo-lipo on the top. It is a phase in that case, and hydro-hydro on the bottom. So this is, so here it adapts. It is interesting, first of all, as a process, but also it means that when you form this is compartments, and compartmentalization was certainly at some stage a very important step in the formation of cellular systems and so on. Of course, it's quite far away from a cell, but nevertheless, the formation of compartments of more hydrophilic and more hydrophobic compartments, this would lead to selection and amplification just by distribution about physical chemistry. This is interesting for some other reason, which I have simplified. I took a slide. If you generate such kind of a distribution between two phases, you can now ask the question, if I add something to one of these phases, what will happen to the other one? In other words, if you have an effector, number 1, which you add in the top phase, you will modify the distribution of objects in the top phase. Since the distribution in the top phase changes, the distribution in the bottom phase will also change. So if you are sitting at the bottom of the tube and look what comes down from up there, what comes down will be a fingerprint of what has been done upstairs. In other words, I have a slide with lots of ions on it. If you add iron on the top, you will change the distribution on the top, and what comes down is different. And it will bear the signature of iron. And of course, this is valid for also for another effector. You can change it. And this has been done for a number of metal ions. And each metal ion has a signature, a sort of an imprint. The interesting thing, and sort of the thing which was sort of a deviation from what we were studying for many years, is that the information is not in a specific interaction. It is just in a distribution. There's an adaptation to an effector, and the message is transferred not through one entity which is transferred, but by a distribution. And this, the message in a distribution is also, for instance, valid in insects. When a male and a female want to find each other, they have different signatures of molecules for insects, and they react, they recognize these distributions, which is the information. So we have spent many years trying to understand molecular recognition, and molecular recognition remains, of course, the lock and key principle remains the basis of that. But nevertheless, the information can be just in a distribution, which is characteristic of the type of object. Sorry. Okay, let me nevertheless just quickly go into that. When we split the phase, then we have two phases which now talk to each other through the interface. And that changes the relations between these agonist-antagonist relationships. I don't want to insist too much on that. It may be a bit confusing at the start. But if you start with a single phase and then split it into two, where the aqueous phase is on top of an organic phase, and then through the interface, things can exchange. And now the AB, which is the best water soluble, is linked to the A prime, B prime, which is in the other compartment. So that when you do something to AB, the other thing which happens is in A prime, B prime, somewhere else, in another space, so to say. And so the relationships are reversed. So what was correct within a given square is now opposite in that square, but it goes from one compartment to the other compartment. See here, AB now talks with A prime, P prime, but not in the same phase in the other one. And this is something then which is sort of interesting. It's like multiplying by -1, what the result. So, compare change to the interface. I'm going a bit quickly here, just because I have something still to say. Again, the fittest drives anti-fittest, but AB is now linked to the other compartment. AB drives amplification of A prime, P prime, but not in the same compartment, in the other compartment. It talks in this way through the interface. Yeah, so you add an effector and you have seen what happens. Okay, let me just go through this. So the information, I insist again, is in the distribution, and it is adaptation to an effector, a message transfer without messenger. Finally, let me go to what I now consider as the thing we are mostly interested in. This morning, Professor Petitjean talked about quadruplexes. And quadruplexes are special arrangement of DNA molecules. But this is the base, that's the base, it's much simpler. Quartets, which are the basis of it, are the result of the formation of a macrocycle, a supramolecular macrocycle here, by 4 guanine residues, which can form a nice square, which is stabilized usually by a metal ion like potassium. Potassium is probably the best one. Okay, we looked at this, and I want to make this story short because the last one will be coming. And when they form these objects, which are flat square units, which can pile up, what they do, they form a hydrogel by columnar stacking. This is well known. We didn't find that. This is something which is well known. Many years ago, I think even in the 50s, Küchelbauer and these people, they had already shown the formation of quartets, although they didn't know the structure, I think, at that time. So what happens? You have this unit. It can form the quartet by hydrogen bonding in a non-Watson-Crick way. Here, the hydrogen bonding, the little dots are the hydrogen bonding. And then once they are formed, they can stack on each other. And that then leads to the formation of a hydrogel, which is shown here. Now, if you introduce in a system of exchanging entities the possibility to form the hydrogel, the hydrogen formation may drive the system, which would be very interesting because a hydrogel is more organized than a solution. So, first result, simple. You have a component which has a guanine residue here, which can form the hydrogel. And you take another one which has a different serine type of structure, which cannot form a hydrogel. And now you let this guy over here choose about the two, between the two. You mix together, and of course we know we predict that the one of the two possibilities, A and B, which is the condensation with either the guanine containing compound or the serine combining compound, the one is guanine can form the hydrogel. So the result is very strong amplification of the A compared to the B, which means that you mix together, and in principle you should get 50-50, but the fact that the hydrogel can form will lead to the strong amplification, the strong selection of the one which gives the self-organization. You can introduce that in a system of 4 constituents. That is just adding another aldehyde, the B prime, and then you get back to this network I described earlier. Then you can look at your solution in the following way. You get a mixture, but by NMR spectroscopy, all the lines which are contained in the hydrogel are broad. Only the lines which are not contained, which are in the water, which is contained within the hydrogel, those are still moving, so have sharp lines. So you can find out that in the solution you find AB prime, A prime, B prime, and A prime B. And of course, by difference, then you know that the one you cannot see is of course what is remaining, because the molecules don't evaporate. And so you find that the gel is formed by AB, which could be predicted, but which shows the principle that organization has led to the formation of the compound which wants to organize. This is the result. AB is amplified. And how do you know that? Because A prime, B prime is amplified. That's agonist amplification, but a reverse way. AB is you know that AB has been amplified because it must be equal to A prime, B prime, since matter doesn't just float around and disappear. So there's the amplification of the constituent which leads to gel formation. A gel is something which is less mobile, more organized, and which you can even calculate the gelation driving force, which is about 1 kilocalorie. And there's a selection driven by self-organization. Now, I want to finish with an example, which is the most recent one, which was done by Hui Gu, another Chinese co-worker, who is now in Shanghai. And because it's the definition of organization can be appreciated by NMR methods. So let's go back to the Knoevenagel reaction. I'm sorry for the name, but I didn't invent the name. It's Monsieur Knoevenagel, who was the one who invented the reaction, discovered the reaction. This is this exchange reaction by forming of this four-membered ring. Yes, this four-membered ring I showed at the beginning, where the imine in red on top, on the right, here, this one, the imine, reacts with this appendix and then exchanges the R2, the ER1 and the ER2, and by this mechanism I showed earlier. So what happens then? The first step is again forming an organized plateau. Here this is well known, this was studied especially by colleagues in Netherlands, that barbituric acid derivatives, they form a nice rosette, they call it a rosette, a six-member hexagon, not a square in this case, a hexagon, which leads to a sheet, a thick sheet, like the one with 4 earlier, but it's now 6. And this sheet is now a building block for stacking, and you get indeed a columnar supramolecular polymer, which is a gel. That means a much more sticky, less mobile state of matter. This can be called also a supramolecular polymer. I had talked only about linear ones, but this is now a stacked one. It's a columnar one, which columnar gels, they exist, columnar polymers exist. So what can we do with that? What can one demonstrate with that? It's a double supramolecular oxidation, okay. Now this is a bit complex, but I just summarize it. Don't worry about the details. Here we mix we have made 4 compounds, 4 constituents, Knoevenagel 1, imine 3, Knoevenagel 3, and imine 1. So they have been chosen, of course intentionally, such that one of them, the 1, K and 3, which bears the long chains, the this chain is C12 chains. That means 3 times 12, 36 carbons. This is very sticky. This has a lot of fingers to stick together, and this is the gel-forming one. So when you then you can look at the system by NMR, and despite the fact that organic chemists don't like broad bands have a lot of information. A broad band means that the mobility of the molecule has decreased. Of course, it doesn't help you very much because you don't see much. But it is well established in nuclear magnetic resonance that when the molecule moves more slowly, bands broaden. And from the width of the band, you can deduce the motions of the molecule, which means the bandwidth, in very simple terms, is a measure of the mobility of the system, the stickiness, so to say. So when you go from, and a gel, of course, when you heat a gel, it becomes a solution. So when you start with, these are just measuring line width, and what I showed, and just being rather simple, when you go from the gel phase to the solution phase, the bandwidth decrease, which means the molecules move, of course, much faster in a solution than in a gel, in a sticky gel, where the viscosity is much higher. And so then you can look at the distribution of the 4 constituents I have shown to you, of the 4 constituents which are up there. And they are here. The percentage of constituents at 2 temperatures, one is above, the one is below the melting point of the gel. As you see, in solution, you have about statistical distribution of 24%. And as you change the temperature just a little to go into the domain where the gel can form, then the gel will form and will induce the redistribution so that you have an amplification of the one which forms the gel, the green one. But the green one automatically leads also to the amplification of its agonist, the purple one. So, yeah, okay, no, not yet. So this shows that the less mobile state, which forms the gel, which leads to the gel, amplifies the one which leads to that gel. It's sort of a system which catalyzes the organization by itself. And so the next step of importance is that if you have too many, this is simple, there are only 4. But if you have now 100 of those components, then this nice selection effects will probably disappear in the washing out by the complexity of the system. There will be not much happening anymore. So you have to, and this is an important step, I find, you have to confine, you have to find a system where you confine some of the, when you make a selection of some of the entities so that they're in other region of space and they do their job by themselves. Then you can again see these simple effects, which are this agonist and amplification, or antagonists. So the way to do it, we have some results, is to create, but just go into a system where you have compartments. And compartments are, for instance, micelles. You add something which can form a micelle. The micelle will then pick up the compounds which like to go into the micelle and leave the other ones out. And within these micelles, you can now see the effects better. They are not washed out anymore by what by the number of let's say numbers don't wash out anymore the features. When you have too much multiplicity, very high multiplicity, what tends to wash out the effects because there are too many things you cannot see it. And so in this case, the multiplicity is then reduced to what is inside the compartment. So let me conclude on that. This is now what I'm mostly interested in, because it's really an important step, self-amplification of organization. If one has to be careful with the terms. Self-amplification, organization amplifies itself. In other words, it's a drive to organization. So we start with the solution, the 1, 2, 3, 4, the red, the blue, the purple, and the green. In solution, they are more or less 25%. You cool down. It's really very simple. It's trivially simple. You just cool down. And when you reach the region where the physical system wants to form a gel, okay, it can form one, but not only can it form a gel, which is what obvious, so to say, but it also modifies the system in such a way that it generates the one which wants to form a gel. It's not just taking a compound, which then when you cool down, if you take a confiture, jam, You heat the jam is fluid, and you cool it down, the jam is not fluid anymore. But here, the constituents which lead to the jamming, so to say, they are amplified because they are in equilibrium, and you amplify that one, which gives the more sticky object. So when you go regions the cell by cooling, the self-assembled unit in green is amplified. Its agonist is also amplified. It may form, it may not form, but it is in principle amplified. This is an increase in order, the organization, order. You heat it, you go back to that, and you can do that as many times as you want. So, what are the conclusions? Oh, too bad that you don't see all of it. I don't know why this has shifted, because on my slides, it's not like this. Anyway, what we can conclude in sort of strong terms, if organization can happen, organization will happen. Or if order can be, order will be. Now this is something quite interesting, which means that in line with the very beginning, that our system is such, our laws of the universe, physicists' laws, thermodynamics are such that order is not an accident. Order is a consequence. The drive to organization is a cosmic imperative. I put a question mark, but of course my answer is not a question mark. My answer is an exclamation mark. And the bottom is, well, what is it again? It's the same thing. Anyway, I don't know why my slides have changed like that. Anyway, I consider that it is a cosmic imperative in our universe. So the next step is cosmology step. Thank you very much for your attention, and I hope that you have been.
Thank you. Thank you, Professor Lin, for his inspirational talk. I think definitely echoes very well at the beginning how you say chemistry is bridging between physics and biology, right? So this is like organization of the molecule through the different aspects. So maybe I'll let the audience ask a few questions to Professor Lin. Don't be shy.
I have a question actually. Usually I do some AI for material chemistry. So my question is, I wonder if such self-organization or self-amplification is some kind of self-supervised or unsupervised learning to driven the phenomena of chemistry.
In AI?
Yeah.
Okay. Look, I mean, AI is a fantastic tool.
Yeah.
And what I said at the end, where we have to use a compartment to simplify things, that is something which can perhaps be treated by massive data analysis and so on. So it could be very interesting to have a look at it. It's too recent, so I encourage you to do so. Because the systems get, there's a combinatorial explosion. As you increase the number of reactive groups, and especially if you take some which are multifunctional, you get an enormous explosion which you cannot handle anymore otherwise. So it might be very interesting to develop systems where you have to find the right parameter to analyze it, like the guys who developed AlphaFold for proteins. They used parameters like distance between given amino acids, which were the correct parameters. I think it probably took them some time to find that. And I think this can be nice. This is a new tool, a very fantastic power. But it's a tool.
Thank you, Prof. Lin. Thank you for the wonderful talk. I really enjoy your talk. Actually, I'm from a department of chemistry. I'm a synthetic chemist, and a major focus of my research is on framework materials, so which utilize the dynamic covalent
what material?
framework materials. Maybe you heard of like covalent organic frameworks or
framework materials. Okay,
yeah, framework materials. So it takes advantage of this like dynamic covalent assembly method to construct the material. Your talk provides a lot of insights.
It's better this way.
Into how to study the formation mechanism of this kind of materials, the self-application based on some external stimuli there. I guess the major stimuli for the formation of this type of materials will be solvents and heat. So I have a question for your systems that because for this page you have 2x2 square here. So you have different building units inside the system, then driven by one type of stimuli, you can control the application between the combination of different species. I'm wondering here is for the synthetic point of view. So I'm wondering why you add a mixture of this. What's the purpose of you have the mixtures inside the system? So if you have just A and B, can you form the hydrogel or maybe the targeted material nicely, or is the other compound is just form behave like an inhibitor to control the reaction rates, and there's any method to study the kinetics here?
Okay, one answer for that for me is that I want to see how if you increase complexity of the material, if you can still see effects which are interesting. I find the effect of organization helping the generation of what organizes is a very fundamental principle. Now, in the case of materials, there are now datamorphs, but there are also dynamic frameworks where the people have developed things with CN double bonds, quite nice ones. What I would be interested in is, in that case, I haven't time to do that anymore, but would be to see if a given organization which can give a sort of a dynamic organic framework would also be generated by the compound which has to get in. That adding the one which can get in will also generate what can bind it. And this would be sort of self-organizing materials. Yeah. I don't think anybody's done that, but the people have done the metal organic frameworks, dynamic ones. Some are not dynamic. Oh, no, most of them are dynamic. They haven't really looked at it as this way. But if the potential unit which is bound can generate what binds it.
Yes. Just when we grow to enhance the single crystallinity of our type of materials, normally sometimes we add an inhibitor which has the same bonding type compared to the framework we want to form. That's why it can control the reaction rate, so it can form a way to decrease the crystallization nucleation rate, that will enhance the crystallinity of the material. So my previous question to you is that study the complexity of the system. So a B prime, A prime in this system, actually they just it's not very useful for helping the material forming, is it? So my question is that what's the role of the A prime and B prime in the system here? Are they really, because you amplify A, B, and A prime, B prime. Yeah. So what is the role of the other?
The other ones then disappear.
Disappear. So let's say
this one go 50-50. There is nothing left for the other.
So if you add A and B, you can form directly the target material itself. Why you mix A prime and B prime into the system? So yeah, okay. So let me rephrase myself. My question is that so if you only have A and B in the system, then you can definitely get A, B, right?
Yep.
So then why you have to add A prime and B prime into the system?
Oh, because we wanted to make a complex system. So we wanted to make these mixtures, and so as to be able to study the behavior of these mixtures.
I see. Thank you so much.
But you had used also an interesting term which I did not at all mention: kinetics. These systems are all at equilibrium, but you also kinetically go through different steps. We have a few cases of that, but that is quite important. At the end of it, thermodynamics always wins. Thermodynamics will win at the end. But on the way, and we are on the way, our thermodynamic state is not a very funny state. So we are, living organisms are on the way. So it's interesting to see also if one can make these kind of systems which change with the kinetics. And there's one person who is now in Nanjing, Mei Xiaohe. She studied when she was with me a few cases where kinetics come into play and where you shift from one diagonal to the other diagonal as time goes.
But yeah,
so kinetics are very important.
Yeah, it depends on the nature of the reaction and the chemistry there, right? So sometimes the kinetics also wins given a specific condition. Yeah, thank you so much.
Bonjour, monsieur. Je me
Bonjour.
sens mieux de te revoir en pleine forme. Okay, so my question is slightly different. So you gave us beautiful examples of constitutional dynamic networks. And as you know, 111 years ago, our friend Alfred Werner talked about constitution and configuration when he was talking about coordination chemistry.
Yeah.
And he's the father of that. Can you give us any example or thoughts on configurational dynamic networks, where we might think of temperature and time and chirality in terms of information?
Yeah, sure. Yeah. That should, I think introducing chirality is certainly a factor of great interest. But it would be interesting to see also if same chirality, that same chirality amplifies itself. That would be quite interesting. There's a chance that it will do it. Yeah. And even now with the work of Soai in Japan, where there's a sort of a chirality explosion. Now, this is something which is sort of startling when you, Soai showed that if you buy a compound which is not chiral, racemic, mixture of left and right, and perform the reaction on it, the one he invented, you get full chirality because, and this Mislow in fact had already spoken about that, Kurt Mislow. This comes from the fact that 50-50 does not exist. You have 49.999, 50.11111, but 50-50 does not exist. There's no chemical, no racemic, which is exactly the same number of molecules. And if you have a system which is amplifying enough, then it amplifies the one which has 3 molecules more. If it is 3 in a million or in a billion, it nevertheless amplifies that one. That is a fantastic result. It's possible. The trouble is we discussed a lot about that, but as I said, Kurt Mislow from Princeton, he died many years ago now, has had, and some for the people in Zurich also, they had sort of talked about that already. And it's an incredible thing that 50-50 does not exist. That is like also in science, there's no 0%, there's no 100%, except in mathematics. No, but it's a very interesting, very exciting point that one can, maybe is linked to some physical property which makes things dissymmetric, non-conservation of parity or something like that.
Okay, so maybe, so I think many of the young scientists or students or postdoc here are not in this area, so maybe I'll just ask a question for them. So what makes you get in, well, I guess they are also searching for their research topic and other inspiration. So what, may I ask, like what drives you into studying this area of research, and what would be a word of advice to many of the young scientists here?
You know, each of us thinks differently. This person, that person, the other persons up there, they are different. So I'm interested in a sort of a logical way of sequential fashion of developing things. And I find that you have to be sort of driven by a goal, something like organization is, we were organized. So organization is a very important factor. I don't talk about, nobody asked the question, what about entropy? Entropy, okay, sure, but we are the result of free energy, delta G, delta H minus T delta S. Without delta H, we would not exist. We exist because of the response energies. What the rest is doing is not our problem. So it's very interesting to try to understand the consequences of the simple thermodynamic factors on complicated systems. And the fact also, the simple fact is quite, once you have the result, it's obvious. You see, this is trivial, that stuff. But the fact that when you do sequential competitions, that you get simpler system at the end, that despite the fact that you have made it more complex, that is also something sort of, that's quite interesting also.
Okay, so maybe we'll...
So there's a lot of things to do. Don't worry.
Great advice too. So maybe we will end the seminar here, and please join me to thank Professor Lane again.
Okay.